Hello everybody and welcome on today's lecture on Introduction to Theoretical Computer Science. Today we will start to discuss algorithms, how we can describe the algorithms and how we can prove that algorithms are correct. So I suppose everybody of you have some idea what an algorithm is and how algorithms could be described. On one level of abstraction, the algorithms could be described as a code in some programming language or even as a machine code that is executed by a computer. On the other hand, we could have some informal descriptions of algorithms in form of sentences in natural language, and it's one thing that we will sometimes use in descriptions of algorithms is so-called pseudocode, which is something in between. Pseudocode resembles code in some programming language, but the main difference is that pseudocode is not intended for a computer to execute, but for a human reader that reads some text, like some article describing some algorithm or some textbook where some algorithm is described and so on. So it's more structured than description in a natural language, but on the other hand there is no strictly specified syntax, so any kind of notation could be used in this description and so on. Yeah? So here we see a small example of a kind of pseudocode I will use in this code. So it describes a function that takes as argument an array and a number that where the value of this number gives the is the length of this array. And the goal of this algorithm, what it should compute, is the maximum value that occurs in this array A. And it's very straightforward algorithm where we start by assigning to local variable k where value 0, where this value k indicates those element of the array that has been maximal so far, and then we in a for cycle we try for values of I from 1 to n minus 1 or elements, and always check if the given element on position A is greater than element in position K, and if it's the case we assign A as the new value of K. And at the end we return the element on the position K in the array. So I suppose it's quite clear this kind of descriptions of algorithms. Yeah. So when we will discuss algorithms, we will concentrate mainly on this kind of algorithms that just take some input and for the given input produce a corresponding output. So we will not discuss or do those kinds of algorithms that would act in some more interactive way, where that would, for example, obtain some output, obtain some input, then produce some output, and again obtain some input, and so on. Yes, in some reactive way. But rather, we will consider only those algorithms that take all input data at the beginning and then produce output as a result. And when we will discuss algorithm, it's in fact not very important from where the data are read and where they are written. Yeah, if they are written maybe from some kind of input device or they are written to some kind of output device, yeah, like file or screen or somewhere, or whether they are read and written from memory and to memory. So from the point of view of analysis of algorithms, these things are typically not important, and we will use except of pseudocodes or some informal description in a natural language, we will also use another kind of representation of algorithms in a form of so-called control flow graph. But before going to this, we can just realize that instruction in an algorithm, or maybe in some programming language, or some imperative kind of programming language, could be typically divided roughly to two kinds of instructions or operations that are performed. One of them are those instructions or operations that perform some work on data. The typical examples are assignment, where we compute a value of expression and assign this value to some variable, or if we have some conditions there. So there could be some expressions in this condition. So evaluation of these expressions, things like reading input, writing output, and so on. So this is one kind of operations. And the other kinds of instructions or statements in some programming language or descriptions of algorithms are things that they do not perform operations on data themselves, but rather specify how the instructions of the first type are ordered, particularly how they are combined together. So something which is so these ways of combinations are called control flow, and this includes things like branching, so statements like if and switch, different kinds of cycles like while, do while, for, and so on. It also includes the sequential composition when we have several instructions and order them into some particular block of code. This also includes things like entering into subprograms and returning from subprograms, and so on. When we will, there are many different kinds of control flow graphs, and we will consider one particular variant where the nodes of the graph are basically some positions between instructions, and before the first instructions and after the last instruction. If I go back to this pseudocode, so there will be a node corresponding to position before this assignment where value 0 is assigned to k, then another position where after this assignment and before the variable I is initialized in the beginning of this cycle and so on. So this pseudocode that was described them, or this algorithm that was described in pseudocode, is here represented in the form of control flow graph, where the edges of the graph are labeled with instructions of this first kind, like evaluation, like assignment, evaluations of expressions, and so on. So this is initial. This is denoted as the initial control state. So these nodes can be viewed as a kind of control states, and these edges can be viewed as some kinds of transitions. So it's like this resembles finite state automata in this sense, and where states correspond to situations where the computations is where some instructions were already performed and some other new instruction should be performed, and the transitions correspond to this performing these instructions. One thing is that branching is here represented in a way where in some nodes we just have just one transition going out of the given state. Yeah, so for example, in this state 0 we do not have any choice and we must perform this is instructions where 0 is assigned to k. Here in state 1 only value 1 could be assigned to variable I, and so on. And in this state 2 we have two branches which are labeled in conditions which are written inside square brackets, and the idea is that those condition that is evaluated to value true could be performed. Yeah, so we typically will assign these conditions to transitions going out of the state in such a way that exactly one, in every situation, exactly one of these conditions will be true. They are mutually exclusive. Yeah, that exactly one of them will be true. Yeah, so either I is less than n or I is greater or equal to n. So depending which of these conditions is true, so this one could be performed. Note also here that for example in this pseudo code here it was not represented explicitly that the value of I is in every iteration of the cycle 4 is I is incremented by 1. Yeah, so here it's more concrete in the sense that we have here this transition that goes back to the beginning of the cycle and increments value I by 1. Yeah, and this is a final state where the computation ends. And just for simplicity, because if we would want to represent this returning some computed value, which is the result of performing this function, we will represent it by using some auxiliary variable that represents some position in memory where the resulting value is written. Yeah? So that's it. So informally we have some idea what a control flow graph is. This kind of representation of algorithms will be useful for some things we will discuss later, and this is in fact quite close to the way how, for example, compilers for programming languages represent internally code where they perform compilation, and so typically they will read the source code, transform it to some kind of abstract syntax tree, and then from this abstract syntax tree, after performing maybe some type checking and so on, it will typically transform it into such form that resembles something like this, and then typically most optimizations and so on are performed on this kind of representation, from which it's then produced corresponding machine code. So this kind of representation is, in this sense, it's quite close to what is often used in compilers for programming languages internally when they process. Just to recall what kind of construction we could represent in this graph, yeah, because this graph allows us to abstract from the details of the particular programming language, or of the way what kinds of instructions or statements are available in a given high-level programming language. So it's more explicitly represented in the structure of this graph. Yeah? So just to get some idea what typical constructions could be represented there. In fact, here I have labeled all transitions with some statement. For simplicity, we could also imagine that there is something resembling epsilon transitions in finite automata. That would be some kinds of go-tos, yeah, just going from one state to another state without performing any kind of operation. So here in this schematic pictures, I sometimes use this kinds of transitions that do not perform any operations. In fact, they could be removed if we wanted, but maybe it's more comprehensible when we use them in these pictures. Yeah, so let's say S1 and S2 are some kinds of maybe some complicated expressions which are itself represented by some kinds of or some kinds of complicated statements that could be represented by some graphs. So we can have some kind of sequential composition of statements where we perform the first statement, and after performing it, the second statement is performed. Or we can have some conditional evaluations of statements, like we start by evaluating conditions. So if the condition, some condition B is true, so then statement S1 is performed, and if negation of B is true, so if B is false, so negation of B is true, so then statement S2 is performed. And after performing any of these statements S1 or S2, we continue with some other to some other states where the computation ends of this statement. Or yeah, so this was a kind of if where we have two branches. We can have also a variant of if with just one branch. When if condition is true, then some operation is performed, and otherwise this some statement S is performed, and otherwise it's skipped. We can have different kinds of cycles, like while cycle or do while cycle, where in while cycle we have the condition B is evaluated at the beginning. So if the condition is true, then statement S is performed, and after performing it, we go back to the to the beginning, and the condition B is evaluated once again, and it would be true, then again S would be performed, and so on. And whenever condition B is false, then the evaluation of this cycle ends, and we jump out of the cycle. And so cycle do while is very similar. The only difference is that here it can happen in while in cycle while it can happen that this statement S is never performed. If at the beginning this condition is false, then this part is never performed. In this kind of cycle, this statement S is performed at least once. So at the beginning it's performed, and then a condition B is evaluated, and if it's true, we go back to the beginning, and otherwise we go out of the loop. Yes, so these were examples of loop. Another kind of loop is for loop, where we iterate over some values. Yeah, so considers such statement where I has values from A to B, and for each of this value there is performed statement S. So it can be decomposed into these smaller instructions or smaller operations that are performed there. Like it starts with initializing variable I with value of this expression A, and then it's tested whether I is greater or equal than B or less or equal than B, yeah, where B is some kind of expression. And if it's less or equal to B, so then this statement S is performed, and after performing S, the value of variable I is incremented by 1, and we go back to the beginning of the cycle, and perform this test once again, and so on. And after and when value of I obtains value which is greater than b, then we go out of the loop. Yeah. So basically this can be viewed as a short way how to write something like this. Yeah. So here it's written in a form of a pseudocode. So where we explicitly write the initialization of I and this increment of I and so on. Yeah. So these are some examples of how some typical kinds of constructions that often occur in programming languages could be represented in such control flow graphs. Maybe I will mention also just another kind of control flow that maybe at first sight it may not be so obvious that in fact it's a kind of control flow, and this is so-called short-circuit evaluation of compound conditions. Yeah. So when we have conditions like in ifs and whiles and so on, when we have conditions which use some combinations using logical connectives like conjunction or disjunction, like and or we can use this kind of evaluation where at first we evaluate the first part of the condition. Yeah, like here we have this combined condition I is less than n and I is greater than x. So we start by evaluating this first part, and if it evaluates to false, then it's not necessary to evaluate this second part, because we can be sure that the whole condition is false. Yeah? So this second part is evaluated only in this case when this evaluates to true. Yeah, so here it's represented in the form of graph. If we would have some if b1 and b2, then as1 and else as2. So condition b1 is evaluated. So if it evaluates to false, then we can go directly to S2 without evaluating this condition B2. And if B1 evaluates to true, then B2 is evaluated, and depending whether it's true, then continue to S1. So to get to S1, both conditions must be true, and if at least one of conditions B1 or B2 is false, then S2 is performed. And similarly for OR, yeah, where at the beginning, if B1 is true, we can go directly to S1 without evaluating B2, and if B1 evaluates to false, then B2 is evaluated, and depending on this, S1 or S2 is performed. There may be a question whether it's this difference is important, yeah? Whether it would not be the same as just having a state where we would have just two transitions, one to S1 and another to S2, and one transitions would be labeled with condition B1 and B2, and the second one negation of this conjunction. Yeah? So not B1 and B2. And similarly for OR, it could make difference whether evaluating this condition could end with some failure, with some kind of error. Yeah? Like let's say we would like to go through an array of length n. So if we would use this short circuit condition, so we can be sure that this subcondition will be evaluated only in those cases where I is less than n. On the other hand, if we would always evaluate both sub-expressions, then if I would be greater or equal to n, and let's say array would be indexed from 0, so it will contain elements on indexes 0, 1, 2 and so on up to n minus 1. So if I would be greater or equal to n, then this condition could fail because there would be access out of the bounds of the array. So typically in the pseudocode and when we will think about evaluating such kinds of conditions, so we will assume that this kinds of short circuit evaluation is used. In fact, as I said, this representation by control flow graph is very close to the kinds of instructions on the level of machine code or assembler or some kind of byte code and so on, where typically all control flow is done by, or realized by two kinds of operations, by unconditional jumps and conditional jumps, where the idea is that we have instructions on some addresses. Like here I started to address them starting from 0, but of course it's not necessary the start of 0. Maybe it's this address specifies some position in memory and the particular order of instructions, and unconditional jump here represented by this goto in standard way, these instructions are performed in such a way that they are performed in the specified order. So if we start on this address 0, so this instruction is performed, then this instruction is performed, then next instruction, and so on. So for the operations like assignment and other similar kinds of operations, we just continue with the next instructions on the next address. But if there is this unconditional jump, so the computation will continue on the specified address. So this L represents some address where the computation will continue. So after this operation, it's not continuing on this address 3, but on this address 6, and conditional jump here represented by this if. So this is other kind of if than we had in this higher level kind of code, using this structured constructions where we have this if of this kind, where this S1 and S2 could be some structured instructions or statements. So here we can have just condition and operation go to. So if the given condition is true, then the computation continues on the specified address in this go to. So the next instruction will be this one. Or if the given condition B is false, then or this condition is false, then the next instruction is the next one. So here in this instruction on address 4. So here I have used this high level kinds of operation. Of course in the machine code bytecode there will be some more lower level kinds of operations. So maybe something which is performed here by one instructions could require several instructions on the lower level. But and of course the particular syntax of how instructions of machine code are written, for example in assembler in a human readable way, is of course typically quite different than this. But the basic idea is that the control flow is represented by these kinds of operations or instructions. And just as a remark, in which is typical, for example, for assembler, if we try to write instructions on very low level, then it's quite common not to write the addresses of the instructions explicitly, but rather to use some kinds of symbolic labels, and then instead of using the precise addresses, to use these labels. Yeah, so this go-to means that we will so instructions could be denoted or marked with a given label, and the computation will continue on the given label. Yeah, if there is go to L3, so the next instruction is this one. So if this is evaluated and if it's true, then the next instruction will be this one, or if it's false, then the next instruction will be this one. I have also mentioned that in assignments in high-level programming languages, we could have some arbitrary complicated expressions. So typically on the low level, these complicated instructions could be decomposed into some simpler kinds of operations. Yeah? So if we would want it, we could decompose them into some elementary operations where every instruction could contain just one, maybe some arithmetic operation like access to an element of an array and so on. Yeah? So let's say if we would have such instructions in a high level programming language, yeah, so of course it may require to introduction of some maybe here I use some variables, yeah, maybe some kinds of auxiliary variables that will store values of intermediate results of evaluating of this expression. Yeah, so this I plus s is assigned to some auxiliary variable t1. Then for example the 3 times j is this value is assigned to some auxiliary value t2. Then this t2 is incremented by 1. Then by this now t2 contains an index into this array b, so the next instruction will be to read the value on this index. Then to this value of variable x will be added. Then this will be multiplied by value of while, and then value 8, constant 8, will be added to this t3, and that at the end this computed value will be returned to array A to position specified by this t1, where we computed that it's on position I plus s. Eh? So I do not say that this is the most efficient way how to compute it, but I just want to illustrate that we typically could decompose more complicated instructions into some simpler constructions. Yeah, so if it's necessary, we could if it would be necessary, we could assume that in the control flow graph all these operations are really very primitive kinds of operations, like adding to numbers and assigning in somewhere, reading some element from a writing an element to an array, and so on. Now I will try to describe what we mean by computation of an algorithm. Yeah, so typically for algorithms we assume that there will be performed by some kind of machine, and what kind of machine this can be, it depends. Yeah, it can be some real computer that executes instructions of machine code, or it can be some kind of virtual machine, yeah, like in Java virtual machine, or virtual machine for Python, or for some other kind of programming language, which can be viewed as some kind of kind of machine which resembles a real machine with a real processor, but is more independent with respect to particular hardware. and performs instructions written in so-called bytecode. Yeah, so it executes some kinds, and typically this execution of these instructions is emulated by performing in software simulating this kinds of operations that are performed by this virtual machine. Yeah. Or so in this sense it's more abstract than concrete hardware that could be used to execute algorithms. And even more abstract would be some kind of idealized mathematical model of computer. But again, we can imagine that this is some kind of machine that performs some kinds of instructions, works with some kind of data. And when we will consider those machines that will perform algorithms, so either we can imagine that the given machine is some kind of specialized machine that is able to execute only one particular algorithm. So this could be typically the case for those idealized mathematical models, when we would just want to analyze one particular algorithm. So we can imagine this machine that performs just one algorithm. Or this machine could be in some sense universal, in the sense that it obtains not only input data, but it could obtain the descriptions of the algorithm in a form of program. Yeah, so if the machine obtains different programs, so it will be able to execute different problems. So these programs are not built into the machine. And what is typical for all, probably all these kinds of machines, even if they are real computers or virtual machines or these idealized mathematical models, is the idea that this machine performs this its operation. It works in steps, in some discrete steps, and we will assume that the machine will process some particular input that could obtain as at the beginning. Yeah, and it could work on different inputs with the same algorithm. So of course there can be many different kinds of these machines, but one possibility, or one straightforward possibility, would be to consider those machines that will remember during its computation. It will use some kind of memory, and it should remember which instruction is currently performed by the given machine, what is currently executed. What is the current instruction, or what will be the next instruction that will be executed, and it will also have some kind of memory where it will store some data. Yeah, so of course it depends on the kind of machine, what are the type of data it works with, and how this memory is organized. And what kinds of instructions could be performed with this data in memory, what can be performed on them. And it also of course depends on the kind of machine, how it works with the input and output. Yeah, whether it has some special way how to read input data from maybe some input device and write output data to some output device, or if we can just imagine that some part of memory is intended for storing the input data, and some part of memory is intended for the writing output data. Yeah, so but these details are are of course important for the particular kinds of machines, but from the some abstract global point of view, they are not so important. And what I would like to describe here is not some particular concrete kind of machine, but rather to give you some general idea what I have in mind. Yeah? So the computation of a machine could be viewed as some sequence, or during this computation the machine goes through a sequence of so-called configurations. Yeah? So again, the configuration, this notion is something which is very general. It occurs in many different kinds of machines, but of course depending on the particular kind of machine, there can be different kinds of configuration. Yeah? So I will try to describe what I have in mind, or what is typically mean by a word configuration of a machine. A configuration is a description of the global state of the machine. Yeah. So what will be the content of its memory, what is currently perform instruction, and so on. Yeah, so we can imagine that we will let the machine run, and we will stop and it at some moment, and we would like to describe its global state that captures all information that is needed for the continuing in the computation. So it is part of this computation of this configuration. So if we would consider those representation using this control flow graph, yeah, like here. So one possibility would be to think about configurations as consisting of two parts. One part specifies what's the current control state, and the second part will specify the content of memory. For simplicity, we will consider memory that will be organized into variables, some named variables that could hold some particular value. Yeah? We will not specify precisely what could be the types of these values. Yeah? We will be slightly general here. We will arrow any kinds of types you can think of, or that will be useful for our purposes. So this content of memory, so if it's organized into these variables, so if we would like to represent this code, so here we have variables like k, I, n, and array a. Yeah? So the content of memory can be like this, that for example LA consists of these values. Value of variable n is 5, value of variable I is 1, value of variable k is 0, and there is also this auxiliary variable result. Yeah, and I have used this question mark to denote that no value has been assigned to this variable result yet. So there is some unknown value. Yeah, so it has not been initialized yet. So this could be a typical example of content of memory that represents value of those variables which are important for this algorithm. We would like to represent a configuration, and the whole configuration will also contain information about the control state. Yeah, so let's say the current control state will be state 2. So we can imagine that during the computation we can have a current configuration where the current control state is state 2, and the content of memory is like this. The values of variables are like the content of variables is like this. So assuming we have some particular kind of machine M, and this machine executes some particular algorithm ALG, and it obtains some input data W, So a computation could be viewed like a sequence of configuration where it starts with some initial configuration which depends on the input data W, and in every step the machine just goes according to this algorithm, where, for example, if we would use this representation by control flow graph, so in every step it will just go from one configuration to another by performing the corresponding instruction, by performing the given transition between these configurations, and it could possibly end in some final configuration where the machine halts and produced the result that was computed by the machine. It will be probably best to illustrate it by an example. So let's consider this control flow graph, and let's assume the input, this input W will be so here we do not use any kind of input or output device. We assume that the input is written in some variables, and at the end it's also we specify some variables where the output is written after the end of the computation. So let's say the input is given by this content of these variables A and N. So A is, let's say for concreteness, that we will have this particular array with variable N contains value 5, which denotes the length of this array. And so the computation starts in some initial configuration, which is here denoted alpha 0. Where the control state is 0, so if we take a look at the control state, so it starts in the initial control state, and the content of memory is given by the input. So these variables containing input contain some value, and the other variables contain some unknown value. They are not initialized. So this is denoted by these question marks. So these variables I, K, and result, so they have not been assigned yet, so they contain some unknown uninitialized value. So the first instruction, or in this control state 0, the only transition that could be performed is performing this assignment where 0 is assigned to variable K and the next control state is 1. So the next configuration will be when the control state will be 1, and the content of these variables A, N, I, and result remains the same how it was, but now the value of K has been changed to 0, so it's now initialized to value 0. So we are now, after performing this first step, we are in configuration alpha 1, and in this configuration alpha 1 there is this instruction that assigns value 1 to I, and the next control state is 2. So after performing this, the next control state is 2, and variable I has been initialized to 1, to value 1, and again the content of all other variables remains the same. And in this configuration alpha 2, so we have control state 2. So if we take a look, we have here, so here we have two possibilities. So depending whether I is less than n, or if it's greater or equal to n, it will continue here or here. So in this configuration we will evaluate the condition, and value of n is 5, value of I is 1, so I is less than strictly less than n, so this condition is true. So in the next configuration the content of memory remains exactly the same like it was before, but now the control state has been changed from state 2 to state 3, and in state 3 we have another condition. So we will test whether AI is greater than AK, or if it's less or equal to. So AI is if we assume that the array is indexed starting from 0, so the value of AI is 8 on this position 1, so it's 8, and value of AK, if k is 0, is 3. So we have that AI is greater than AK. So this condition is true. So the next control state will be 4. Again, the content of the memory remains the same, and here in state 4, the only possibility how to continue is to assign value stored in variable I. It's stored into variable k. Yeah? So it's evaluated this expression consisting only of variable I, and this value is stored to variable k. So I has value 1, so the new value of k is 1. So the next control state is state 5, and the value of k has been changed to from 0 to 1. All other variables remain the same. And in state 5, this assignment is performed where the new value of I is computed as I plus 1. So value I plus 1 is assigned as a new value of variable I. So current value of I is 1, so 1 plus 1 is 2, so the new value of I is 2, and the new control state is state 2. And so on. Yeah. So again, it's tested that I is less than n, so 2 is less than 5. So the next control state will be state 3, and the content of memory remains the same, and so on. Yeah. So I will just show the remaining configurations. Yeah, and maybe at the computation ends in this final configuration where the control state is this final control state 7. So the algorithm has halted, and the content of memory is like this. Yeah. So the output value is stored in this variable result. So this input consisting of this array A and value n was at the beginning was stored in these two variables. So this given us this initial configuration alpha 0. The algorithm then performs several steps and ended in some final configuration where the value is stored in some variable in the variable result. Yeah. So the resulting value that was computed by the algorithm is value 8. Yeah, so computation is such sequence of configurations, and if alpha and alpha prime are two configurations, so by using this notation we can denote that during the computation in configuration alpha, by performing instruction I, the machine goes from configuration alpha to configuration alpha prime. Yeah? So for example, here we had configuration alpha 0, and by performing instruction where assign 0 to k, by performing this instruction, it went to this configuration alpha 1. Yeah, in configuration alpha 1, then by performing this instruction, the machine went to this configuration, and so on. Yeah? And the instruction also can be this instruction I can be those instructions where some condition is tested. Yeah, so it could be like it was tested that this condition is true. So this led to change of the current configuration. So in general, if we will use this kind of notation, yeah, so computation could then be written like this, that it starts in some configuration alpha 0 in the initial configuration depending on the input, and then by performing this instruction it went to some other some new configuration alpha 1, then by performing some other instruction it went to configuration alpha 2, and so on. And this computation could be either finite, where the last configuration is some final configuration like here, yeah, so this was the case here, where the machine has halted, or it could be infinite, it could continue forever and never reach some final configuration. Yeah, so it will go to some new configurations and run forever. Yeah, so again, this notion of computation, that where we have configurations where by performing some kind of instruction or operation the machine goes from one configuration to another, and when we start in the initial configuration and performs these steps and and either halts after some final number of steps or continues forever. So this is something which is very general and does not depend on the particular kind of machine we consider. Yet this is something which is common to many kinds of machine, but of course the particular details of this what forms these configurations, what they are like, depends on the particular kind of machine. So basically those computations of a machine could be viewed in two different ways. Yeah, so on one hand they can be viewed as a sequence of configurations, what we had here, or they can be viewed as a sequence of operations that were performed. Yeah, so like saying that there was 0 was assigned to k, then 1 was assigned to I, then it was checked that I is less than n, then it was checked that AI is greater than AK, then value I was assigned to k, then I was incremented by 1, then again was checked that I is less than n, and so on. Yeah, so we have these two complementary views of computations of a machine, so either as a sequence of configuration or a sequence of instructions, or we can view it in this combined way, where from one configuration by performing instruction it goes to another configuration, and then performing other instruction to some other configuration, and so on. Okay, so now we come to rather important question of correctness of an algorithm. Yeah, so what we mean by correctness. So basically, when we have just algorithm, and if we would know how computations of this algorithm, how they look, how the instructions are performed, and so on. So it still makes no sense to say that a given algorithm is correct. Yeah, if I would have just some particular algorithm, so it makes no sense to talk about the correctness of the algorithm itself. This notion of correctness always refers to some to a notion of a problem, or algorithmic problem. Yeah? So at first I describe what we will mean by an algorithmic problem. Yeah, so problem is a kind of specification what should be computed by the given algorithm. Yeah, so description of a problem will consist of description of the inputs or input data, description of the outputs. So description what could be input and what could be output, and how these outputs are related to given inputs. Yeah, so of course there can be many levels of abstractions how precisely we define the specification of the problem. Yeah, so on one hand we can say it on very high level without specifying precise details, like saying we will consider problem of sorting where the input consists of some sequence of elements, some array of elements, and the output is another sequence of elements that contains exactly those same elements as the sequence on input, but now ordered from the smallest to the biggest. Or so we have this description of input and output, and what should this output data satisfied with respect to the given input. But in more detail, we could specify the particular format of this input data, yeah, how they are represented and so on. Yeah, so if we would need to consider some more detailed analysis of the working of the algorithm, so it could be necessary to describe the particular way how this input and output data, how they are encoded. But this is something which is often not so important in the analysis of algorithms. So but here we will see a slightly more concrete description of the problem that we try to solve by this very simple, extremely simple algorithm, yeah, which is the problem of finding the maximal value in an array. So I will describe in a moment. Yeah, so on one hand we have this problem. Yeah, so problem specifies what should be computed, what could be input and what should be computed, and what the output should satisfy. But the specification of the problem does not specify how we could obtain this output data. So algorithm is then detailed description of a particular procedure how we can obtain this output data from the input data. Yeah, so algorithm could be this described in, again, as we discussed, on many different level of abstraction. So let's go to particular example. Yeah, so return to our algorithm, this one, and let's specify a problem that should be solved by this algorithm. Yeah, so here we assume that input is given by an array A, which is indexed from 0, and some number n that represents the number of elements in the given array A, yeah, represents the length of the array, and that we will also assume only those inputs where n is greater or equal to 1, yeah, that we will not consider empty arrays. Yeah? So here now this description is slightly more detailed, and it explicitly avoids this boundary case of empty array. So it's supposed that the given algorithm should work correctly only on non-empty arrays, and we also specified how they are stored. That we will use this particular array A and this particular number n to represent the input. And of course we could just informally say that we want to compute the maximal value in this array, but if we would like to describe in more detail, in more precise way, so we could say, for example, that we want to compute some value result, which will be the maximal element of A, which means that this value result that would be computed by the algorithm should satisfy these two conditions, that it should be greater or equal to every element in the array. Yeah, so for every j where j is greater or equal than 0, equal to 0, or strictly less than n, it should hold that aj is less or equal to result, and it should satisfy the condition that the computed value really occurs in the array. Yeah? So there should exist some index j in an array such that the element on this position is equal to result. So this is the specification of the problem. Yeah, so it does not specify how this result should be computed. It's just specify input and output and how they are related, what this resulting value should satisfy with respect to the input. And there is one notion which is often used in this context when we talk about instances of the problem. So by the notion instance, we mean some concrete example of input data for the given problem. Yeah, so in this specification of the problem, the description of the input is general. It allows many different arrays, many of different lengths containing different values, and one particular example of this input, yeah, like input consisting of array A consisting of values 3, 8, 1, 3, 6, and where variable n has value 5. So this particular input data are called instance of this problem. So and for the given instance of the problem, yeah, so basically the description of this input describes the set of all possible instances of the given problem, and for each instance the algorithm should compute the resulting value that should satisfy this condition. So for example, for this instance the output should be 8. Yeah, so this value 8 really satisfies that this is greater or equal to every element in the array, and it really occurs on some position in an array. In general, it can be the case that for a given instance, it's often the case that for a given instance there is exactly one output value, but there are also problems where we can have many possible output values. Yeah, like if we would have for example problem of searching the shortest path in a graph. So in this problem it could happen that there could be several different shortest paths. Yeah, so maybe any of them could be the correct output. So now we have seen what we mean by this notion problem. Yeah, so this is description of the input and output. So it basically describes the set of all possible instances and what are the possible outputs for these instances. And now what we mean that when we say that a given algorithm is a correct solution of the given problem, or that algorithm solves the given problem. Yeah. So if we would have some particular algorithm represented in some particular way, for example by using this control flow graph or using some pseudocode and so on. So let's assume we have some algorithm and some particular problem. Yeah. So problem is the description of the input and output, as we have seen. So the given algorithm solves the given problem if for each possible instance w that is allowed according to the specification in the problem P, it should be the case that when the algorithm runs on the given instance w, yeah, so by running algorithm on the given instance we mean that for given instance we have a corresponding initial configuration of the algorithm, and then the algorithm performs a computation and so it performs some computation. So it should be satisfied that this computation always halts after some finite number of steps, and the second condition is that what is the output which is generated for the given input W corresponds to the specification of the output in the problem P. Yes, so the correctness of this algorithm means that if I take arbitrary instance for each instance, it should be the case that if I would have instance that satisfies this or that corresponds to this specification of possible inputs, it should be the case that after a finite number of steps, this algorithm, for example, will halt and will produce a result that will satisfy this condition. Yeah, so what is important that it should hold for each instance. So then we say that the given algorithm solves a given problem, or that a given algorithm is a correct solution of the given problem. Yeah. So maybe it can be useful to think about those cases where some algorithm is not a correct solution. Yeah? What can happen? What could be the reason why some algorithm is not a correct solution? So there are basically three main possibilities that could occur that mean that the given algorithm is not correct. So if algorithm is not correct, so it means that there exists some input W, some particular input W, which is allowed according to the specification of the input, such that if the algorithm will perform a computation on this input, so one of three bad things happens. One bad thing that can happen is that depending on the kind of machine, it can be the case that some kinds of operations cannot be performed in some configurations. Yeah, like there could be considered some kind of illegal operations or incorrect operations that lead to some kind of error. Yeah, so it could be things like division by zero, or if we access to an element of an array out of bounds, or if we would have some pointers to memory, so we would if we would have some uninitialized pointer that would be 0, and we would access this memory pointed by this, or something like this. So of course it will depend on the particular kind of machine or programming language we will continue. Yeah, so we will use. So in some languages the result could be throwing some kind of exception, or it could be some kinds of segmentation fault, or performing some nonsense, some incorrect operation where like in programming language C, where maybe some unrelated part of memory is overwritten with some random value, or something like this. So this is again not so important now when we think in this high level way. What is particular reason and how what will the algorithm perform in this case? Yeah, so this is one kind of things that could be bad, where the algorithm performs some kind of illegal operations which is not allowed for the given kind of machine. Another reason or another bad thing that could happen is that the algorithm will perform the computation. It will compute some value. It will produce some output and halt. But it will produce some output value that does not correspond to the specification of the problem. So for example, if we return back here, so if we would have some algorithm that would, for example, obtain this as an input and produced a value 6, for example, as an output, so it would not be correct because this condition would not be satisfied because 6 would not be greater or equal to 8. Yeah? So, or if it would produce value 17 for this input, so again it would be something which is incorrect, because even if this would be satisfied, it would be the case that this value 17 does not occur in this array. Yeah? So so the case when the algorithm runs on the given input without without occurring any kind of error, but the produced value does not satisfy the specification of the output. Yes, so this is the second thing that could go wrong, and the third thing that could be wrong is that there is some input for which the algorithm performs some steps perform some computation, but this computation never halts. Yeah? So we will have this infinite kind of computation where it will go to new and new configurations forever and never halt. It will never stop. So so this is so possibly maybe it loops or something happens like this. Yes. So these are basically the three main reasons why some algorithm is not correct. So either it could perform some illegal operation, or it can produce some incorrect output, or it does not halt. Yeah? So of course, when we write some algorithm or when we construct some algorithm for solving some particular problem, so it could be it's a standard thing to use to try the working of the algorithm on some particular instances, and to check that on these instances it works correctly, that it halts and produces the expected output. And of course, we could have, if we would use maybe some systematic way, trying to many input instances, so we can be more sure if it works correctly on them. But in fact, using this testing, we can just discover some bugs. Yeah? So if we have some particular input for which the algorithm does not behave as we expect, yeah, so either it crashes because of some error, or it produces some output which is not expected, or runs forever. So if we have some particular example of such input instance where it does not work correctly, so we are sure the algorithm is not a correct solution. It contains a bug, and it must be corrected. Yeah. So testing allows to reveal bugs in algorithms, but so it can show the presence of bugs. But in fact, by this we cannot show that the algorithm behaves correctly for all inputs. Yeah, because typically, like here, we have infinite number of possible inputs or input instances, or even if we would put maybe some bounds of the length of the array, and some bounds maybe on values that could be stored into this array, and so on. So it would not be, the number of instances would not be infinite, but still would be maybe astronomically big. Yeah? We would consider arrays of length 1 billion and values that could be stored there from -2 million to plus 2 billion. So so there could be some astronomical number of possible inputs, and it's or typically if we think on more abstract level where we do not put any bounds on the amount of memory we have available, so we have infinite number of possible inputs. So of course it's not possible to use testing in the sense that we would try all possible inputs and we would check that for each possible instance the algorithm behaves correctly. Yeah, so this is something which is not manageable. So we must proceed in some other way. Yes, so typically when we have some algorithm, so quite often is this algorithm equipped with some kind of proof of correctness of the algorithm. Yeah, it's probably typically in practice it's not the case for such simple algorithms like algorithm like we have here. Yeah, for computing maximal value in array. This algorithm is very primitive, so there is probably not necessary in practice to check correctness the way I will describe in a moment. That would require the proof, but if we have more complicated algorithms, so typically it requires some kind of proof that somehow increases how sure we are that the produced output will be correct, that the algorithm will behave correctly on all possible inputs. Yeah, of course we never would have 100%. We will never will be 100% sure that the algorithm is correct, because there could be some bug in the proof also. Yeah, so but when we have some kind of proof of correctness, we are maybe much more sure that the algorithm is correct. Yeah. So typically, so I will now try to describe how these proofs of correctness, how they could look. I will show it on this very simple algorithm, yeah, but of course in practice it's used on much more complicated algorithms, and I will show it in a quite big level of detail, which is not often the case. It's in the practice to show it on such level of detail, but I will try to show it to give you the precise idea of how the correctness of the algorithm could be proved. So it's quite common or quite convenient to divide the proof of correctness into two separate parts. The first part will prove so-called partial correctness of the algorithms, which basically means that we will show that the algorithm never does something wrong. And by doing something wrong, we mean performing some kind of illegal operation, or if it produces some output, that the output will be correct. It will never produce some incorrect output. Yeah. On the other hand, in this part we will not ensure that some output will be produced. It's possible that the algorithm and it will not also ensure that the algorithm halts. Yeah? So in this first part we will ignore the question whether the algorithm halts after some final number of steps or not, but we will ensure that if it runs, then none of these bad things will happen. On the other hand, the second part of the proof then consists of showing that for every possible input, the algorithm will halt after some finite number of steps. Yeah. Again, in practice, depending on the particular algorithm, it can be the case that some of these parts could be trivial, yeah, or quite obvious, so maybe it would not be necessary to give a precise detailed proof of it, but in general, both things should be proved if we should be sure that the algorithm behaves correctly. Yeah? So let's concentrate at first on this first part. Yeah. Let's concentrate now to showing that the algorithm does not perform anything wrong. So one notion which is quite useful for this is the notion of invariant. Invariant is some kind of condition that is always satisfied during the computation, and typically this invariant is related to some particular position in a code. Yeah? So if we imagine the representation in a form of control flow graph, so we could imagine we will have some invariant referring, for example, to this state 2 or some other invariant connected with this state 4 and so on. Yeah, with any of these states, we could have different invariants for different states, and the idea is that if we would consider all reachable configurations, yeah, where reachable configurations are those that could be reached in some computation. Yeah, so configuration is reachable if there exists some particular input W, such that if the algorithm runs on this input W, so during the computation it goes through this configuration alpha, or so the set of all such configuration that could be possibly reached in some computation, so such configurations are called reachable, and between these reachable configurations, yeah, so these configurations or for all possible inputs, we can consider, for example, the subset of those configurations where the current control state is state 2. And the invariant is then some condition that is satisfied for all these reachable configuration with the given control state Q, yeah, like this control state 2, for example. Yeah, so whenever the algorithm will be in a configuration, for example, in this state, so then the given invariant will be satisfied. Yes, so this is some condition on the values of variables in memory, or the content of the memory of the machine in those configuration which are where the control state is the given control state. So I will illustrate it in a moment. Yeah. So basically, of course, we could describe these invariants informally in a natural language, but basically, they are something that could be described using formulas of predicate logic, where free variables in these formulas correspond to the variables of the program. Yeah, so the variables in memory. So if we had there these variables a, k, I, and a result, so this could occur as free variables in the given formulas. Yeah, so formula could be, for example, very simple formula is like this. Yeah, so here use the standard mathematical notation. Yeah, not the precise syntax of predicate logic. So predicate symbol less or equal to is represented in this using this infix notation and using the standard symbol. But formally, it's or it can be viewed as a formula of predicate logic. Where the interpretation corresponds to the meaning of these predicates and functions I would use in this in these formulas. So here I do not use any functions, but I use here this constant one. So it's consider interpretation, but it's interpreted in standard way. So let's say, for example, the values of the variables could be integers. So this value 1 is interpreted as integer 1, and these I and n are now variables where when we consider evaluation, which is determined by the content of these variables. So if we would have a configuration where, for example, value of I is 5 and value of n is 14, so it basically gives us a current valuation under which this formula could be evaluated. So now for such formulas it makes sense. Interpretation give us what's the meaning of this less or equal to and so on, or some other kinds of relations and functions that would be used in the formula, and valuations now correspond to for each configuration during the computation of the machine, for the given configuration there is a corresponding valuation under which the given formula could be evaluated, and it could be either true or false under the given interpretation and valuation. So this is an example of invariant. So this invariant basically says that the value of variable I will be always between 1 and n. It will be greater or equal to 1, and it will be less or equal to n. So let's say if I would have this graph, so I could say that, for example, for this I could have invariant that in this state this invariant will hold. So in every computation on every possible input, it will be always the case that whenever the algorithm is here in this control state, then this condition is satisfied. So this is what we mean by invariant. But of course, it's I can state something like this, but it's not obvious that it's really the case. So we can formulate the given invariant, and then we could check that or not, maybe not just one invariant, but maybe several invariants in the code. In the extreme case, we can specify invariant for each control state, and then we could check that these invariants are correct. I will describe in a moment how this could be done. So let's consider this control flow graph representing this program. And let's say we would like to show that in fact what could go wrong in this kind of code, probably the only let's assume for simplicity that we do not put any bounds on the values that are stored in variables. So the values of variable, let's assume the values of variables could be arbitrarily big. If we would put some bound on the maximal and minimal values that could be stored to variables, then it would need some more detailed analysis would be required for this. But for now, for simplicity, let's assume we do not put any bounds on the values of variables. So they could be arbitrary integers. So one thing that could go wrong is the access to if we use the indexes of arrays. So we assume the only correct or those indexes that could be accessed are those from 0 to n-1. So if the value of index would be something less than 0 or greater or equal to n, then it would mean that this would be a illegal operation, that we access this array out of bounds. And let's say we would like to show that this is not the case, that this never happens during the computation of this algorithm. Yes, so one possible way how we can do it is to try to formulate as hypothesis for each of these control states some invariants that would specify the relationships between the values of variables in the given state or in the given position. Yeah, and let's say for state 0 we will have this formula phi 0, for state 1 we will have this formula phi 1, for state 2 formula phi 2, for state 3 formula phi 3, for state 4 formula phi 4, and so on. Yeah, so I will do it in a very high level of detail. Yeah, so this is something which is not typically done in practice when we do it by hand or not by some kind of computer tool that would check these invariants. But if we would use just pen and paper, so this is typically not done on such level of detail, but here I will illustrate it because I want to give you the precise idea how this proof of correctness of these invariants, how it looks. Yes, so we start by specifying this invariants. So probably at the beginning we cannot say nothing about we cannot say anything about values of I and k. We can just be sure that n is greater or equal to 1, yeah, because we assume that at the beginning this according to specification of the input. Yeah, if I go back here, we assume that we consider only those input where n is greater or equal to 1. So at the beginning we are sure that n is greater or equal to 1, and if we take a look at the graph, so this value n is never assigned. We never assign to variable n anything. Yeah, so it remains the same during the computation. So this invariant will hold until the end, and for example, in state 1, after value k has been assigned value 0, we can be sure that here always value of k will be 0. Yeah. On the other hand, but for example here we cannot be sure that the value of I will be 1, because the value of I could be incremented here. Yeah, so if the algorithm goes several times through this cycle, so value of I could be 1, 2, 3, and so on with each iteration. Yeah, and but whenever, yeah, so it's so we can just know that how the algorithm works, and we can know that whenever the value of I is n, so the algorithm continues here. Yeah, so this construction of this construction of this invariance is not something that could be done in a completely arbitrary way. Yeah, in fact there are ways how it could be automated to some extent, but at least some of these invariants must be typically specified by some human person that tries to check the correctness of the algorithm. Yeah, so this is not something that could be generated completely in a completely automatic way. So this is something that typically requires some insight into the working of the algorithm. Yeah, but if we try to think about how the algorithm works, and I suppose this is something every programmer does when he thinks about the algorithm, he maybe implicitly could think about such invariants that hold in some positions of the code. Yeah, so here the value of I, so one quite probable hypothesis here is that something we would require would be that that value of I is between 1 and n, and it could be equal to 1 and equal to n. Yeah. By the way, I will use this kind of notation instead of writing it like this. Yeah. So I view it as a shorthand for this. And in a similar way, we can note that this value of k will be always inside the cycle will be some value which is strictly less than I and which is greater or equal to 0. Yeah? So maybe we will formulate such things. In fact, in states 3, 4 and 5, yeah, inside the cycle, because we go inside the cycle only in case where I is strictly less than n, so here we will have invariants that value of I will be always strictly less than n in these 3 states. Yeah, so again here we have a strict inequality, and in state 5, because there is this assignment, so it could happen here that value of k is could be also equal to I. Yeah? So if it goes here, so here k will be strictly less than I, but so if it go here, it will still be strictly less than I, but if it goes through this branch, so it could be equal to I. Yeah, so let's say we formulate this invariants like here. Yeah, so here I write them as formulas using conjunctions where I combine several conditions, but in the following I will often use this shorter way how to use this with commas. Yeah, so by this I mean that all these subconditions are satisfied in the given state. Yeah, so basically this formula is a conjunction of this, but to make it more slightly more readable, I will write it like this. Yeah, because if we determine several conditions for the same control state, so basically the invariant holds there is the conjunction of this subconditions. Let's say we have formulated this for every state in the control flow graph. We have formulated such invariants, but so far they are just hypotheses. What we think that should hold in each configuration in the given control states. So if we now have this these hypotheses about invariants that hold in different states, so there now could be a way how to check that these invariants really hold in all computations, and the idea is that we just need to check each edge, each transition in the control flow graph. Yeah, so for each edge we check that, for example, if I would have configurations for this state 1, and there would be some invariants, so if I assume those configurations where the given invariant is satisfied, so it's just necessary to just ensure that after performing the given instruction by which the given transition is labeled, then we go, then the next configuration will be such that the invariant for the given control state will be satisfied. Yeah? So the whole proof, when we at first consider all possible configurations, is now decomposed into checking into smaller parts when we check just performing one very elementary operation, yeah, like performing one assignment or checking one condition. And if we would check that assuming that the given invariant holds before performing the given instruction, then it also holds after the given instruction. And if we check it for every instruction in this control for graph, if we check it for every transition, so we can be sure now that and of course we must check ensure that the invariant for the initial state will be always satisfied at the beginning. So if this will be satisfied at the beginning, and so we have configuration where the given formula phi0 is true, then after performing it we will obtain configuration where some formula phi1 will be true. Then after performing next transition formula for state 2 will be satisfied, and so on. So if we have proved that assuming that the invariant was true before performing operation, so it will be also true after performing the given operation. So we can be sure that in any configuration that could be reached during the computation, we still will be in those configurations where these invariants are satisfied. Yes, so basically it can be viewed like this, that each invariant, in fact, between all possible contents of memory, selects those configurations where the given invariant is satisfied, and by proving that these invariants are maintained, we ensure that all reachable configurations form some subset of these configurations that correspond to the given invariants. Yeah? So so the algorithm could not get to some configuration where some invariant would not be satisfied in the corresponding control state. So in particular here in this example, if we would check that all these invariants are correct in this sense, so then we could be sure that there is no excess which would be out of bounds, because in fact the only access to arrays is here and here. So in state 3 we have condition that I is greater or equal to 1 and strictly less than n, so it will be correct index into array A, and k will be strictly less than I. So if I is less than n, so k will be also strictly less than n, and it's greater or equal to 0. Yeah, so again it will be a correct index into the array. So we can be now sure, or so far we cannot. Yeah, we have not checked that these invariants are correct. But if we would show that these invariants are correct, so then we will be sure that there is no excess out of bounds here in state 3, and another access to array is here in state 6, where we read from this position. And in state 6, if there would be true that k is greater or equal to 0, a string to less than n, so again it would be correct access. So there would be no access out of bounds. So now the question is how we check something like this, that these invariants are maintained. Yes, so I have already described that the idea that we consider all transition, and for each transition we will check that assuming that the given yes, so if we would have an edge from state q to some state q prime, which is labeled with instruction I, and if this state q would have some invariant expressed by formula phi, and this state q prime some invariant expressed by formula q prime, then we must ensure that assuming that if we would have some configuration where the current control state is q and together with some content of memory, yeah, so if there would be some configuration alpha, then by performing this instruction I, it will go to some configuration alpha prime where the control state will be q0. Yeah, so whenever the machine goes through this given edge of the control flow graph, so in this configuration alpha, assuming that this phi holds in alpha, then in this new configuration alpha prime, this invariant phi prime will be true. So let's consider at first the case which is slightly simpler, which is the case of those edges which are labeled with some test of condition. Yeah, so an edge like this or like this or like this. It's simpler because the content of the memory is not changed by this transition. They only evaluate a condition and check that this is true. So as an example, consider this transition from state 2 to state 3. Yeah, and there is test that I is less than n. So in such case, in fact, we assume that phi is true in state q, and we perform this test, so we can be sure that after performing this test that the content of the memory satisfies this condition. Yeah, so we must just check that assuming that phi is true and this condition is true, then the new invariant is true. Yeah, so that this implication holds. Yeah, so it must hold for all possible values of variables. So basically we will check a formula that such formula is true in the given interpretation. That yeah, so if these would be all variables we consider like n I k, that for each value of n and each value of I and each value of k, if this original invariant is true and also the condition is true, so it's the given transition is really performed, so the new condition will be true. Yeah, so for example here, if I would consider this transition from state 2 to state 3 with condition that I is less than n, and if I go back to this invariant, so in state 2 we assume that if we assume that in state 2 these conditions are satisfied, and moreover we assume that I is strictly less than n, so it's quite obvious that from this we can derive this here, because if n was not changed, if it was greater or equal to 1, so still it is, the value of k and a were not changed, so if this was true, so it will be true also after the transition, and if this was true that I is less or equal to n, but in addition we also assume that I is strictly less than n, so from this we can derive that this must be true. Yeah? And similarly, in a similar way, for example, if here in state 2 we have this formula phi 2, and we would like to check that this phi 6 holds after performing this, so from state 2 to state 6, assuming that I is greater to equal to n, so this condition for n is it remains the same. Yeah, but if we assume that I is less or equal to n, and at the same time that I is greater or equal to n, from this we could derive that it's rather the case that I is equal to n. And if we now know that I is equal to n, and we had before that k is greater or equal to 0 and strictly less than I, so if I is equal to n, so k must be strictly less than n. So yeah, and so on. We could do it for or other conditions. And I will not do it. I just want to illustrate the basic idea, but we will not do all the details. You can try it yourself to check these conditions. So consider now those instructions where we have some kind of assignment, yeah, like for example this transition, or this transition, this transition, or this transition. Yeah, so let's consider, for example, this one where the value I is assigned to variable k. So in general, and we will concentrate now only on assignments, yeah, as just to illustrate the basic idea. We will not discuss all the details for any kinds of operations. So we will consider those assignments where we of the form where on the right hand side we have some arbitrary expression which is evaluated in the current configuration, and the computed value is assigned as a new value of some variable x. So now this operation or instruction modifies content of the memory, because it changes the value of x. It does not change the value of any other variable. So basically what we need to do in checking that, assuming that some invariant was true before performing this instruction, and then after performing it some other instruction be satisfied, so it's probably necessary to distinguish the value of x before the operation and after the operation, before performing the instruction and after performing the instruction, and just for this checking, yeah, not in invariance, but in checking that this instruction preserves this invariance. Yeah, so let's consider. For this purpose, I will denote the value of variable x before the instruction. I will use just x, and use x prime for the value of instruction after the operation. Yeah, so for example, if I would analyze this particular transition, so I would distinguish value k, which would be value of k in configuration here, and value k prime will be value of variable k after in the next configuration. So if phi is the invariant that holds in the state before the instruction, so after the assignment we can be sure that the new value of variable is the given by evaluating this expression e, which corresponds to the original configuration, the values of variables in the original configuration. So we must show that the values of variables, that they satisfy some condition that corresponds to the new configuration, but if this invariant refers to this variable x, yeah, like here to like here, for example, if it would refer to variable k, so we must, in this invariant, when we check this edge, we must ensure that in this invariant, in this new state, we refer to this new value of k. Yeah? So let's take this formula phi prime and let's substitute all occurrences of x, or we rename of 3 occurrences of x with this variable x prime. Yeah, so if I would have assignment like this, where the new value of k is computed as 3 times k plus I plus 1, so the formula would look like this. Again, it must hold for all possible values of variables. Yeah, so if I would have these variables n, I, k, so for each value of n, in value of I, and each possible value of k and a k prime, it holds that whenever the original invariant holds, that refers basically only to these variables and to this original value k, and assuming this invariant, and assuming that this new value of k, this k prime, is equal to the value that is computed using this original value of k, then the formula that represents the invariant in the next state, but where occurrences of x were remain x prime. Yeah, so here where occurrences of k in phi prime, occurrences of k were renamed to k prime. Then so we must ensure that this implication is true. Yeah, that whenever this will be true, then this will be true. Yeah, so if I return to this example, and if we would, for example, consider this edge from state 4 to state 5, an assignment where I is assigned to k, so from state 4 to state 5, so in this phi 5, instead of this phi 5, we would consider the formula where this k would be replaced with this k prime, and k prime would be equal to I. Yeah, so assuming that this is true, and assuming conjunction of this and conjunction with condition that k prime is equal to I, then we must show that this is true where instead of k here we would have k prime. Yeah, so this implies this implies this part implies this, and if the value of k is equal to k, then it's surely true that k is less or equal to I. As another example, because here this right hand side of the assignment does not include this k. Yeah? So let's consider this edge where we have I on both sides. Yeah? So from state 2 to state 5 to state 2. So if we assume this, and if we assume the value that I prime is equal to I plus 1, so we would like to ensure that this phi 5 implies this variant of phi 2 where I would be renamed to I prime. So if I was, for example, n was not changed, so it remains greater or equal to 1. If I was greater or equal to 1, so this I prime will be also greater or equal to 1, so this part will be true. If I is strictly less than n, so then this q prime, which is I plus 1, will satisfy that it could be greater or equal to n. Yeah, so if I have some value that is some integer value with the strictest more than n, and add 1 to it, so it could be equal, less or equal. And if k was greater or equal to 0, so k was not changed by this, so it remains the same. And k was less or equal to I, so but if the new value of I is I prime is I plus 1, so k will be strictly less than this I prime, strictly less than this I plus 1. So these were again just examples of these two edges, but if we would do the same thing for each edge, each transition in the given control flow graph, we would check that these invariants are really correct. So we can now be sure that there is no excess out of bounds of the array, but it still does not ensure these invariants. If we would know that they are correct, we cannot be sure that the algorithm will produce a correct result. Yeah, so but we can use the similar idea. We could just extend this invariance. Yeah, so I have written here some new invariants denoted psi0, psi1, and so on up to psi7 that also talk about the content of array A and how it's related to values of variables. What is satisfied there? Yeah, basically it says that so it includes all these conditions like before, all this, but we will add the requirement that for example in these states the k refers to the maximal value in the part of the array from 0 to I. So using a similar arguments as before, similar kinds of arguments as before, we could check that these conditions are really true, and we could check that assuming that if we would check that all these invariants are true, then we, in state 7 we'll hold this invariant that basically corresponds to saying that the value in variable result satisfies these conditions we had here in the specification of the problem. Yeah, that the value of result is greater or equal than each value in the array, and that it occurs in the array. Yeah, basically. Yeah, so for each j where aj is greater or equal than 0 and less than 1, then aj is also equal than result, and there exists some j that satisfies this. So if we check all these invariants, and in particular we check the invariant that holds in the final state, and check that this invariant implies the conditions that were specified in the specification of the problem, what the output should satisfy. So we can be now sure that whenever the algorithm will get to the final state, then that will surely produce a correct result. Yeah, but by checking the invariant, we have not ensured that the algorithm will really halt after some final number of steps. Yeah, because it's possible now, so far as we know, if we would know that these invariants are correct, so we would know that for every computation the algorithm will go through configuration where these invariants are satisfied, but it does not ensure yet that the algorithm will halt. Yeah, so before discussing this, I just mentioned what I already said before, that typically in when we do proofs which are intended for people to check, yeah, when we just try to informally give arguments of the correctness of the algorithm, it's much more common in literature, in articles or in textbooks that describe some algorithm. It's not common to provide such detailed descriptions on invariants in every control state, but rather to concentrate on some important states. And what I mean by important, these are typically the states where the algorithm enters to loop and where it performs iteration in these loops, and where it goes out of loops. sorry, those spaces where we enter into loops, and that we must go through in every iteration of the loop, and where the algorithm goes out of the loop. And typically we must just satisfy that the algorithm is satisfied when we first enter into the loop, that after assuming that the invariant is true before performing the iteration, so it will be true also after the iteration, and then when we go out of the loop, then it's still satisfied. Yeah, so typically for this algorithm we consider here, so such important state is state 2, yeah, because this is the place where we enter the loop and when we go through in every iteration, and where we also jump out of the loop. So we could, in a slightly more informal way, we could just specify the invariants that hold in this state, or we can say several invariants, or they can be viewed as a single invariant that is a conjunction of this condition. Yeah, so what is important, then that value of n is greater or equal to 1, that value of I is between 1 and n, and it can be equal to 1 and equal to n. Value of k is greater or equal to 0 and strictly less than 1 in this position, and that k points, if we consider the part of array from 0 to k, including 0 but excluding k, then all these elements there, that the k points to the maximal element in this part of the array, yeah? That it's greater than every element in this part of the array that has been processed so far, and that because k is between 0 and I, that it really belongs to this part of the array. Yeah? So if at the end, so we will ensure that at the beginning k is 0 and I is 1. Yeah, so this processed part of the array consists of just this element on position 0, and after every iteration we add one element to this process part, and at the end, when I will be equal to n, so the whole array will be processed, and k will point to the correct to the maximal element in the whole array. Yeah? So this is more common to give such kind of less formal arguments where we just specify these most important parts of the invariant, and we will specify them only for those important states. Okay, so let's go now to the second part of the proof, where so far we proved that nothing bad happens during the computation, but this argument so far do not ensure that the computation will really start. So in general, when we consider some arbitrary algorithms, so basically there are two possibilities while what can happen when algorithm does not hold. Yeah, one possibility is that some configuration is repeated during the computation. Yeah, so the algorithm goes to some configuration that performs some steps and goes back to the same configuration. That the content of variable is completely the same, and the control state is completely the same as in some configuration before. So in such situation, the algorithm will start to loop. Yeah, it will just go through these configurations again and again forever. Or other possibility that could sometimes happen, that we do not have this kind of looping where the same configurations will be repeated, but rather the algorithm will go to some new configurations. Yeah? So for example, it could happen in fact only in case when we allow some infinite kind of memory. Yeah? So because if we would have some restricted amount of memory, so there would be only a finite number of possible configurations. But if we would allow, for example, some dynamically allocate some data structures, or if we allow arbitrarily big values of integer variables and so on. So then we could have infinite number of different configurations. So it can happen that the algorithm will produce new and new configurations. Yeah, for example, it will allocate new and new memory and produce some computation and perform some computation on it and continue forever. And it's often the case that it's quite obvious for the given algorithm that it will have. Yeah, for this for our extremely simple algorithm here in this example, it's probably quite obvious that the value of I starts with 1 and it's incremented in every iteration, and after it reaches n, the algorithm will go to the state 6 and to state 7. So it will have. Yeah, so it's not typical to use again to use the kind of proof I will show here, but I will show some idea which is quite general and that can be used in those cases where is not so obvious that the algorithm has. Yeah, so the basic idea is as follows. The idea is that there must happen that if the algorithm has that during the computation some kind of value is decreased or increased. Yeah, so we will concentrate on the case decreased. So maybe we could again this is something that requires some insight. Yeah, this is not again something that could be generated automatically for every code. So we can try to think about some value which is decreased during the computation. It is not necessarily a value of some variable. Yeah, it can be something that could be computed from values of several variables, but if we have some particular configuration, then from this we can compute some value for this configuration, and if we would choose such value, that we will ensure that in every step this value is decreased. And if it would be the case that this is something that cannot decrease for an infinite number of steps, yeah, so if the values of this the possible values of this amount, yeah, would belong to some set, I have denoted here W, to some set W. So if I would specify for each for each configuration to compute some value from this set W, and if I would find some ordering of values in W, where I would ensure that in every step, when the machine goes from some configuration alpha by performing instruction I to some new configuration alpha prime, if it will be ensured that this value will be decreased. Yeah, so the assignment of these values from this W will be to configurations will be denoted like this. Yes, this F alpha denotes the value which is assigned to configuration alpha. So if the new value will be strictly smaller, but if it will be the case that there are no infinite strictly decreasing sequences of elements in the set, so then I can be sure. Yeah, and by the way, it's in fact only I can concentrate only those configurations that are reachable. So it means if I would have already computed some invariants, yeah, so these reachable, and I would ensure that these invariants are satisfied, that they are preserved during the computation. So I can concentrate only on those configurations where these invariants are satisfied, because the reachable configurations are just subset of them. It can be, in general, it can be difficult to compute the precise set of reachable configurations, but what I can consider some kind of over approximation, some possibly some bigger set of those configurations where the where the invariants are satisfied. So I can concentrate only on these configurations, and for them specify this assignment of these values which are decreased. So it would be the case that there would be some value assigned to the initial configuration, and so some step will be performed. So I will obtain some smaller value. After reaching some new configuration, I will have an even smaller value, smaller value, smaller value. So if it's the case that for the given set and given ordering, there are no infinite strictly decreasing sequences where the next element is always strictly smaller than the previous one, so it would mean there cannot be an infinite computation, because infinite computation would produce an infinite decreasing sequence of values from W. Yeah, so if it would be sure that there is no such decreasing sequence, so it would be sure that there is no some infinite computation. Yeah, and if the invariants are preserved, so this computation cannot end bad way, so it must end in the final state, correctly in the final state. So what could be this set W? Yeah, probably most intuitive would be to use natural numbers, yes, because the natural numbers obviously have the property that we cannot have infinite strictly decreasing sequences. If I would start with some natural number 1000, for example, and I would obtain some smaller number, it cannot go infinitely, because if I cannot go to negative values. Yeah. On the other hand, for example, integers would not be a good set for this purpose, because there could be the infinite decreasing sequences. Yeah, I could have sequence -1, -2, -3, -4, and so on. And also, for example, if real numbers, positive real numbers, also would not be a good example of such value, of such set, because I could have sequences like 1 divided by 2, 1 divided by 4, 1 divided by 8, 1 divided by 16, and so on. Yeah, so there could be infinite sequence of real numbers that is strictly decreasing. Yeah? So natural numbers are examples with standard ordering on natural numbers is something that where we cannot have this strictly decreasing infinite strictly decreasing sequences. By the way, these kinds of sets with ordering are called well-founded orderings, or well-founded sets. And they play quite an important role in mathematics in general. Yeah, but we will not discuss all these details of these formalisms of this. I just want to give you the basic idea. Yeah. In fact, what could be sometimes slightly more convenient than to use natural numbers would be to use a set of vectors of natural numbers, where we would define ordering on these vectors in such a way that we will use a lexicographic ordering. So if there exists if we consider these vectors from left to right, and we find the first position where they differ, yeah, like here, if I take this vector and this vector and this vector, so 5 is the same, 1 is the same, and 3 and 4 are different. So this is the first position from the left where the values are different. So those vectors where the value on the given position is greater, so this vector will be greater. Yeah, so we will in fact could even consider vectors of different dimensions, yeah, with different number of elements, yeah, like here of dimension 5 and here dimension 4. dimension 4. So this vector is greater because 4 is greater than 3. Yeah? So we use this this kind of ordering. Yeah. So where all values to the left on these differing values are the same, or if one of vectors would be prefix of the other, so we would consider this one to be smaller than this one. Yeah, if there is no differing position, but this one is shorter than this has dimension 3 and this has dimension 4, so this one is considered bigger. Yeah, so let's consider this kind of ordering of vectors. So the set W will consist of the set of these vectors. It can be in fact proved that there are no infinite strictly decreasing sequences in the set of all these vectors. Yeah, again, we will not do it formally because I just want to give you the basic ideas. But this is something that can be used for this purpose. And let's consider once again our simple example of algorithm, and let's consider function f that assigns two configurations depending on the current control state, assigns the corresponding value. Yeah? So for state 0 it's a vector of dimension 1 containing just value 4. Yeah? For state 1 it's vector 3. For state 2 the value of the vector will have dimension 3, and the first element will be 2. The second element will be computed for values of variables n and I by taking so for example, if n is 5 and I is 2, so the second element will be 3. Yeah, for such configuration alpha, and so on. Yeah, so let's have this assignment, and what is really required is to show that for each edge in the control flow graph, for each transition, that if we would have a configuration where, and again, as I said before, we could just concentrate on those configurations where the invariants we computed previously are satisfied. So assuming these invariants are satisfied in the given configuration, so when we will compute, for example, if we will consider this transition or this transition or this transition and so on, so let's say we will consider this transition. So if we assume, so for example from state 4 to state 5, so assuming that we have configuration where the value is computed like this, we will go to configuration where the value will be computed like this. We will always obtain a strictly smaller vector by this step. Yeah. So for example, for this transition, this modifies k. Yeah? So value of n and I is not affected by this. So this value remains the same, and the value 2 remains the same, and 1 was decreased to 0. So we will surely obtain a smaller vector because this 0 will be smaller than this 1, and the first two elements will remain the same in this vector. Yeah, so it's probably quite easy to check it for most transitions. In fact, the basic idea is that the first element in each vector gives some value which is decreased globally like this, that we start with value 4. Yeah, because it's quite obvious in this algorithm that we start here, then perform these two transitions, then several times we go through this loop, and then at the end we go like this out of the loop. Yeah, so here the value is 4, here is 3, here inside the cycle it will be 2, this first element, and here it will be 1, and here it will be 0. Yeah, so and what is in fact decreased during the iteration here, yeah, with each iteration, what is decreased is the difference n minus I, yeah, because I is increased and n remains the same, so the value n minus I is decreased with each iteration. So in different iterations, this second value inside the loop will decrease with iteration, but inside one iteration we could be here or here. So here we have value in 5, we have 0, 1, 2 and 3. Yeah? So this third position basically corresponds to the position inside the given iteration. Yeah? So if we will now check or transitions, yeah, so from 0 to 1, 4 is decreased to 3, from 1 to 2, so 3 is decreased to 2, so these values are not important for this. For this transition from 2 to 3, the first two values remain the same because no value is modified, and 3 is decreased to 2, so it's okay. From this transition or for 3 to 4, 2 is decreased to 1, or from 3 to 5, state 3 to state 5, 2 is decreased to 0. Yeah, again, these values remain the same because none of these variables n and I are modified by this. From state 4 to state 5, this is what we already considered. Yes, there's a value. This one is decreased to 0. And from this state to this state, from 2 to 6, this 2 is decreased to 1. Yeah, so these values are not important because 2 is decreased to 1, and from 6 to 7, 1 is decreased to 0. Yeah, so from 6 to, in fact, the only transitions we have not considered so far is this one, and this is probably the most complicated one to check that this really decreases the value, because now this is complicated because the value of I is modified, and we compute for state 5 and state 2. We must consider the value of I before the assignment and after the assignment. Yeah, so we have configuration if I is the value of, if we have the value of variable I before the assignment, so we would have some configuration with this vector, and if we go from state 5 to state 2, so this I here refers to the new value of I, which is the original I plus 1. Yeah, so it will, we could denote it as some I prime and say that I prime is equal to I plus 1. So the first element of the vector remains the same, 2 remains the same, but if we, instead of, we had some original value of I, and we would have this new I prime which would be equal to I plus 1, so n minus I plus 1 is n minus original I minus 1. Yeah, so we had decrease in this second position, so even if this changes from 0 to 3, so it does not increase because this value will be decreased on the second position. Okay, so that's it for today. So we have seen the way. So what was important today was the way how algorithms could be represented, possibly by pseudocode or by this control flow graph, and the notion of computation and the notion of configuration during the computation, and then the way how we could prove correctness of the algorithms, and there was very important this notion of invariant, and then the algorithm holds the idea that some value is decreased in every step. So thank you for your attention and goodbye.